Okay, well, welcome back. In today's lesson, we're going to work on Pythagorean theorem and its converse, the converse of the Pythagorean theorem, which we'll see in a minute really means we're effectively going to use it backwards. And we'll talk about that in just a minute. Pythagorean theorem, as we're already very familiar with, is used for right triangles. So in any right triangle, the sum of the squares of the legs equals the hypotenuse squared. And we know it as a squared plus b squared equals c squared, where c is the really critical one. C represents the hypotenuse, which by definition must be the longest side of that triangle. And as long as we get c in the correct spot, we can work this out. So again, typically we've been using Pythagorean theorem when we know two sides of the right triangle and we're looking for that third side. Plug it in, work it out. So just as a quick reminder or refresher, and I'm not going to do all of these, but for example, in question A, we want to make sure that we identify our hypotenuse opposite the right angle. And at that point, a squared plus b squared equals c squared. A and b are the two legs. They are interchangeable for our purposes at the moment. And we're going to find c. Now we can call it c, x, or maybe they give us an expression, x plus 9, whatever, 3x. Whatever it is, we plug it in and we work it out. So we're going to just do some quick math here. We have 9 squared for 81. 16 squared is 256. And that equals c squared. Of course, we're going to add 256 and 81 for 337 equals c squared. And remember, to get c by itself, we need to take the square root. So we're going to take the square root of both sides to get c on its own. So we hit our square root button, and at that point, we follow directions. Here it says round to the 10th. So our answer here is going to be 18 point, and it's going to round up to 0.4, 18 and 4/10. Now, again, the critical thing is getting things substituted in the correct spot. Just for the sake of review, let's do question D. I'll just bring the work out here. The hypotenuse is 17. We're looking for this leg. It's A or B, it doesn't matter. So I'm going to just call it X for our purposes. So again, we have leg squared plus leg squared equals hypotenuse squared. So that gives us x squared, 8 squared for 64, and 17 squared is 289. Of course, we're going to follow our rules of algebra. We subtract 64 from both sides, and we get x squared equals 225. And again, we need x, not x squared, so we take the square root, and x equals 15. So again, the hypotenuse must be the largest side. So in my first example, the biggest leg was 16. The hypotenuse has to be bigger. I can catch a mistake if I'm attentive to that. In the second example, the hypotenuse was 17. I'm looking for a leg. It has to be less than 17. And I can feel good about 15. We also worked with radicals, and that's going to be a big deal for us as we move forward. So we might have to work with problems in radical form. So again, let's just do an example here. We'll do question A. Whoops, sorry about that. We'll do question A. We'll just bring it out here. Again, our hypotenuse is what we're looking for. We can call it CX. It doesn't matter. So the first side we can say is maybe square root 15. Now we're going to remember, it's the leg squared plus the leg squared equals the hypotenuse squared. So make sure that you're using parentheses for your substitution and you're following the order of operations. Square root 15 squared is 15. Square root of 10 squared is 10. And that equals x squared. So the fact that we've been reviewing our radicals is really important. Of course, we're going to take the square root and we get simply a 5. Now, we don't need the radical symbol here. It's just a 5. 5 is the hypotenuse, and that is a bigger number than the square root of 15 or the square root of 10. To check that, if you wanted to make sure, you can always put square root of 15 into the calculator. You're going to get 3.9, and that's definitely less than 5. Now, we have to work with radicals. We can't convert them to a decimal and work with them. But just to confirm which is a bigger number or smaller number, we can do that. Obviously, square root of 15, the square root of 16 is 4. So if it's 15, it's a little bit less than 4. It's going to be 3.9. And again, just for the sake of a second example, because the more comfortable we are right now, the easier the new part of this is going to be. We'll do another question. Again, I'll just do D. We're looking for that leg. So we have one leg squared plus another leg squared equals the hypotenuse squared. And we want to work out these radicals carefully here. 5 square root of 3 squared is 75. 5 square root of 10 squared is 250. Now, again, just a quick reminder with the radicals. For example, 5 square root of 3 squared. That means we have 2 of these parentheses. Numbers on the outside multiply. Numbers on the inside multiply. Then we would simplify that square root, and that's how I'm getting 75. So we can work this out by hand if we're not consistently comfortable with our calculator. Of course, we're going to follow through, and we're going to subtract our 75 from both sides, giving us x squared equals 175. And of course, we have to take the square root. Now, the problem here is that we're working with radicals and our answers have to be in radical form. So I cannot just put this into the calculator. I'm going to have to work this out. Now, I can do my factor tree. I can recognize that 175 is 25 times 7. And 25 is 5 times 5. So I'm looking for that perfect square. And that comes out as a single number. The 7 stays home, and that's x. And again, if I needed to, I can certainly put 5 times the square root of 7 in a calculator, get the decimal equivalent, do the same with 5 square root of 10, just to make sure I get a good feeling which number is higher or lower. Obviously, the square root of 10 is higher than the square root of 7. So I can just think it through and have a little bit of confidence. Okay. So again, working with Pythagorean theorem, something we've been doing for a while, but a quick review there. Now that brings us to the converse of the Pythagorean theorem, which converse effectively just means we're going to do it backwards. The Pythagorean theorem said, do I have it written? No. The Pythagorean theorem said, if it's a right triangle, then a squared plus b squared equals c squared. Converse means we're going to switch it and say, if a squared plus b squared equals c squared, so we're going to plug in all the numbers. And if that worked, then we can be confident that this is a right triangle. So let's say we know the 3 measurements for the sides, and now we need to figure out, is it a right triangle? We just plug in the numbers and work it out. Again, C is the critical number. We have to get the highest number for C. So if we look at an example here, we're given three values. The first thing we want to do is find the highest number and put that in for C. And now we worked it out. So this one worked. It's true. A squared plus B squared equals C squared. We can now determine that those three measurements will form a right triangle. And that's all the converse is. We're testing the three numbers to see if they form a right triangle. If they form a right triangle, great. If not, then we're going to make a determination. Is it acute or is it obtuse? We won't know the exact measurements, but at least we'll know if it's acute or obtuse. Everything we do, we try to add a little bit more information. So let's try just a couple, we'll just do a quick example or two. The first thing I want to do is find the highest number, because that has to go in for C. So now I could do something like 15 squared plus 20 squared equals 25 squared. Now remember, we're testing this. We're asking ourselves, is this true? So we have 225, 400, 625. Add the left, 625. That does equal 625. So yes, this is true. So yes, we have a right triangle. Just for the sake of argument, let's see what it looks like when it does not work out that way. I'm guessing this one's not going to work. I don't know. We're going to find out. So the biggest number. So we have 18 squared plus 34 squared equals 39 squared. And again, we are testing this. So let's grab our calculator. 18 squared is 324. 34 squared is 1156. And 39 squared is 1521. Well, let's see. 1156 plus 324 is 1480. So we can see this one did not work. This is false, which means no, not a right triangle. So it's not a right triangle. Well, now we're going to observe those results. We're not going to do any more work. We're going to observe these results to make a determination. Is it acute or obtuse? Those are the only other options we can come up with. So let's look at how to do that. Again, no more work, just a new piece of knowledge. If we want to determine whether it is obtuse or acute, we want to focus on that C squared value. And you can certainly read over this slide. Think about the C squared value. If it's too long, it pushes the angle open. If it's short, it pulls the angle in. So visually, what I want you to think about is, if we have a right triangle, this C value is the perfect size. Well, what if that C value was too long? It would open this angle up, making it obtuse. So the flip side of that is, what if the C value was too short? It would pull this angle in, making it acute. So we're going to focus on that C squared number. Okay, and I have that kind of explained in a few different slides here, but here's the work. Again, we're going to make sure that the highest number goes in for C, and we're going to work it out. And we can see that this did not work. This is not a right triangle. what we're going to do is we're going to make the comparison of the C value. That C squared number is bigger. Since the C squared big number is bigger, C squared is too big, then the angle's too big. And keep that relationship. If the C squared number is big, the angle's big, right? When they're equal, the C squared number is the right number, so it's a right angle. When the C squared is big, the angle's big, obtuse. When the C squared is small, the angle's small, acute. Very simple relationships connecting the angle and the side that is opposite it. In our example here, the C squared number is smaller. So when the C squared number is small, the angle is small, meaning acute. And that's literally what we're doing here. Yep. So let's, again, do an example. Let's choose letter A. So I'm going to do A over here. The biggest number is 28. So I have to get that in the right spot. So 20 squared plus 21 squared equals 28 squared. And again, this is a test. So question mark, testing it, whatever. 20 squared, we have 400. For 21 squared, 441. 28 squared is 784. Let's add them up. We get 841, 784. So this is not a right triangle. Well, what is it? We're going to focus on the C squared number. C squared is smaller. That means the angle is smaller. Smaller than right. So this is an acute triangle. We'll do one more over here. I see some radicals, so we'll do one more. And again, the biggest challenge is which number goes in for C. I have to make that decision, and I have to get that part correct. So what I might do, one easy approach is change it to a decimal, again, just to compare. You cannot work with it in decimal form, but I can make that comparison. So let's do question E. I'm going to bring the work out here. Our numbers are 8, 16, and 7 root 5. So what I'm going to do is I'm going to go to my calculator, and I'm going to find out what the 7 times the square root of 5 is. And it's 15. This number right here is 15.65, which means 16 is my C. That's the only reason for doing that. Now I have 8 squared plus 7 square root 5 squared equals 16 squared. And this is what we're going to test. So we have 64, 7 square root 5, following up on our work from before, that's 245, and 16 squared is 256. So we have 245 plus our 64, 309, 256. And again, look at that C squared number. Since it is smaller, this is an acute triangle. Okay. If that number was bigger, it would be obtuse. Let's see. Do I have one that's obtuse? I don't know. I do not have these answers memorized, so I don't know. Let's see if we can get one that is obtuse just for the sake of seeing it. 18 squared, 34 squared, 39 squared. So 18 squared, 324, 34 squared, 1156, and 39 squared, 1521. So let's see, maybe this one will work out to be an obtuse, just so we can see an example of it. 1480, 1521. Good. Again, since they're not equal, it's not right. The c squared number is bigger, and that makes this an obtuse triangle. All right, so the c squared is bigger. That means the angle is bigger than right. So bigger than 90, making it an obtuse triangle. Okay? So we have the converse of the Pythagorean theorem, and we're using that to classify the triangle as acute, right, or obtuse. Okay, let's do some practice with that, and we will pick up with the next lesson.